Welcome to the virtual classroom of Chembase School of Chemistry. Sound clear? Right, we'll start on the lesson. We were discussing at last the polymerization. In the last session, I explained what is a polymer, which is an organic macromolecule. A large organic macromolecule formed by many small molecules joining together, and as for these molecules, they are referred to as monomers. So the monomers join together to form polymer. That's referred to as the polymerization. The process of monomers joining to form the polymer is referred to as polymerization, right? So I explained there are two types of polymers. One is addition polymer and the other type is the condensation polymer. Addition polymer and condensation polymer, two types of polymers, addition and condensation. I explained the difference between the two, right? So as for the addition polymers, they are the polymers which is formed where the monomers combine via addition reaction, and there is no byproducts produced during addition polymerization, and in most cases same type of monomer joins to form the polymer. So we discussed in the last session few addition polymers like polyethylene, polypropene, polyvinyl chloride, polytetrafluoroethene. As for the condensation polymers, it is formed as a result of the monomers of two different types of monomers joined together. The main factor in a condensation polymer is that a condensation reaction takes place. A condensation reaction takes place, meaning condensation meaning addition followed by elimination. So in short, we can just say elimination reaction takes place, which is where the two monomers join together to form the polymer, right? So that's the introduction to the two types of polymers, and I explained last week how to write the draw the structures for polyethylene and polyvinyl chloride, right? And also I explained how to identify the repeating unit, right? How to identify the repeating unit, and the short way of writing the polymer, the drawing the structure. All those was discussed in the previous session, so I'm going to skip that part. And also when a polymer is given, how to identify the monomers, the repeating units, and reduce their structures, right? And I think I completed up to page 6, question 9. From question 10 onwards, I had to complete, right? Question 10 onwards, I had to start now, right? So before I start question 10, did I explain the question 9? We did draw the polyesters and polyamides, right? How their structures are formed in the block diagram. I explained in the last session how the ester and the amide linkage give rise to the condensation polymers. Condensation polymers, two or more different types of monomers combine via elimination reaction, and here I'm going to explain to you using the block diagram how these monomers combine. So I'm going to start with the ester linkage. We have studied esters in the previous session, where dicarboxylic acid reacting with diol. Now this is the carboxylic acid reacting with alcohol. I explained how the ester link is formed. This box represents a carbon containing group, so it's a different group. That's why I'm going to color one box and keep the other box blank. So what happens, the carboxylic acid gives the OH and the alcohol gives H. Water molecule is lost, and then these two molecules combine together to form the ester linkage. I know we did this question before, but I just want to make sure you remember how the linkage is formed. So you should be able to identify the ester linkage. So this can continue, right? This can continue to form the polymer. So this is the ester linkage over here. That's very important. You identify the ester linkage, right? So this is how the ester is formed This is the ester link, right? This is O8, the ester link. And this particular polymer, it can continue on both sides, right? As for the amide link is formed when a dicarboxylic acid reacts with diamine. So you have a dicarboxylic acid. You can just draw in a box notation, that's allowed because you're not supposed to know the structures. This is dicarboxylic acid and reacting with diamine. Diamine meaning two amine groups, and amine is known, group is NH2 group. So I'm going to color this box and then eliminate a water molecule, same like what you did for the ester. OH from the carboxylic, H from the amine, a water molecule is lost, and then you get the final product, which is which you see the amide linkage. Let us try to understand how to identify the amide linkage, right? So this continues. I'm going to put dotted lines to show it continues, right? The OH is removed on this side. So this is the amide or the peptide link, which we discussed in the last class. This is the amide or the peptide link. Clear? So if you can identify and understand how these two linkages are formed during esterification and during amide formation, the formation of polyamide, which is condensation polymer, then it will be easy upon you to understand the details of the polymerization. Is it clear? Okay, right. So let us apply the principles of condensation polymerization to understand how the polyester is formed between dioic acid and diol, and also we'll try to understand the repeating unit. Now, when it comes to addition polymers, I explain how to name the addition polymers. We use the prefix poly before the name of the monomer when naming the polymer, because addition polymers are in most cases homopolymers. Homopolymers meaning only same type of monomer combines to form the polymer. So if the monomer is ethene, the polymer will be polyethene. If monomer is propene, the polymer is polypropene. The monomer is vinyl chloride, the polymer is polyvinyl chloride. That is for the addition polymers. When it comes to condensation polymers, we don't use the name of the monomer when naming the polymer, because there are two or more different types of monomers combined when it comes to condensation polymer. So therefore, what we do is we use the linkage to name it. So if there are many ester linkages formed, we call such polymer as polyester. Polyester meaning many ester linkages, because we cannot name the polymer based on the repeating, based on the monomers, because there's no one monomer. So if it's polyethene, ethene is the monomer. But when it comes to the ester, two different, it's a condensation polymer, therefore two or more different, in this case two different monomers combined. So therefore we cannot use the prefix poly before the name of the monomer, but rather we use the prefix poly before the name of the repeating, the linkage. So I'm going to first show you how this is done. So let me draw the structure of dicarboxylic acid and then a diol, right? So this is my dicarboxylic acid. You can just draw a box, because we don't know the different dicarboxylic acids are present. So what is inside the box is carbon containing group. So n number of dicarboxylic acid, this is dicarboxylic acid, or can say dioic acid. That's how we name carboxylic acids, reacting with n number of diols. So I'm going to just color one box. You can color either box you like. Diol, this is diol, two ols. And then what happens, as I explained before, the elimination. The OH is removed by this H, right? A water molecule is lost. Always what gives the alcohol gives the H and the carboxylic gives the OH. That's very important you to remember that, right? Because you might wonder now why we are so concerned about who gives what. Because the reason is if they mark the oxygen of carboxylic acid as O16 and the oxygen of the diol as O18, then what happens, you will not know when where the O16 goes and where the O18 goes. Here Niroshan, Kenan has raised the hand, so I'm going to enable his microphone. If you have a question, just quickly. Yes, Kenan, I can hear you.
Sir, how to do the raising hand?
Already, you have already raised the hand, right? There's an icon to raise the hand. Don't just raise the hand. If you want to speak to me, raise the hand. Otherwise, if the question is, if it's clear, or you can type, then you can type the shorter question. Niroshan, what you should do is check your sound. Let me check where I can speak to Niroshan. He has an issue now. So you have a dicarboxylic acid and a diol. Like what I explained before, the OH is removed from the dicarboxylic at one end, and the H is removed from the alcohol end. So when OH is removed with the H, you get a water molecule. That's why I explained at the beginning how the ester link is formed. So when this is done, the n number of dicarboxylic acid and n number of diol, many dicarboxylic acid, many diol, it results in a polymer. So how this polymer is formed? That is formed with the help of this linkage, the ester linkage. Let me draw what happens when these two combines, right? When these two combines, you can see how the ester link is formed. I'm drawing now the ester linkage, right? This is how the ester link is formed. This is the ester link. Whenever ester link is formed, a water molecule is lost as a byproduct, right? And then this will continue. This is a dicarboxylic acid and one end, so this will be bonded to diol, and the diol will be bonded to another dicarboxylic, so it continues, and then the dicarboxylic acid will be linked to another diol, then that will be linked to dicarboxylic acid, so that will continue to form the ester linkage, a polyester. So you can see, yeah, of course, this corner OH also will be removed. So this is one dicarboxylic acid combining with a diol. Then that diol and the other end, it will combine with the dicarboxylic acid. The OH is removed, and on this end, the OH is removed. The dicarboxylic OH goes with the H of the diol, and the H of the diol goes with the OH of the dicarboxylic acid. So it's a continuous process. It's a continuous process, right? So diol, dicarboxylic, diol, dicarboxylic, right? So each time a diol meets dicarboxylic, a water molecule is lost. As a result, the ester link is formed. As a result, the ester link is formed, right? Is that clear? So you have many ester linkages formed here. That is a polyester, right? That's how we call this whole thing as a polyester. I need to draw at least 3 repeating units here. So I'm going to draw 3. Yeah, Omer. Your question?
Sir, what is the thing next to the HO on the left side?
This one? This is
No,
N.
on the left. Yeah.
This is N. N means many.
Okay.
Right? That is many diol molecules. Right? Because in polymers, not just one combine, many combines. So I'm going to just represent 3 repeating units here. 3 repeating units. Just 1 second. I'm going to start with the dicarboxyl. So OH is removed. So I'm going to draw a few lines here and put C double bond O. And then you have, this is a dicarboxylic joining with a diol. and then again dicarboxylic alternates, and you got the diol again, and then you got the dicarboxylic again, and then I'm going to just end with a diol, because just to get an understanding how to end this polymer, because I'm starting with the dicarboxylic and ending with the diol. And you notice each time ester link is formed, a water molecule is lost, that is the byproduct, right? And you see many ester linkages. These are the ester linkages. I'm going to highlight the ester linkage now. Ester link. This is one ester link, and this is another ester link. So it's a polyester. Polyester meaning many ester linkages, right? Carbon has 4 bonds here. Actually, there is one bond. This is bonded to something, so which is another oxygen. So which is not shown because I can't. I'm going to just show only few repeating units. You can notice here this part from here to over here is one repeating unit, and from this point to this point another repeating unit. So I have shown 3 repeating units in this polymer, right? 3 repeating units is shown. So if I'm to show represent the above structure of the polymer as one single structure, what I can do is I can just draw one repeating unit. This is the repeating unit. When it comes to a condensation polymer, a repeating unit is just basically one of each of the monomer. One of the each monomer together is one repeating unit. So this is the repeating unit, and I put N here to get the short form of the above polymer structures. If I'm to draw only the repeating unit, then it should be only dicarboxylic acid and the diol just once. Just forward all your questions. I will attend to the questions once I complete the explanation, right? So this is the repeating unit. So it comes to condensation polymer, not like addition polymer. Addition polymer repeating unit was one single monomer. So in condensation polymers, it is basically one of each monomer is the repeating unit, and if you put N, then you get the polymer. You can no need to copy while I'm explaining. I'll give you time to copy. So we'll see the questions now. 1 second. Who has raised the hand? Okay. Yes, another question, yeah.
Sir, what is meant by an Ester link?
The ester link is the linkage. When this OH is removed with this H, these two molecules will bind together. These two molecules will bind together. So that bond is what is shown here. When this oxygen, C double bond to oxygen, bonds with this oxygen, that linkage is what is shown here. So that is known as the ester linkage. Yes, the polymer will have the N. Yes. Any other questions? If not, you can copy this now. Polyesters, many ester linkages is the condensation polymer which is formed by the reaction between dicarboxylic acid and diol. The common name of the polymer is called the polyester. Polyesters are used in the manufacture of synthetic fibers in clothing, curtain material, and it's a good thermal insulator. You can copy the structure now, and while copying, if you have other questions, you can forward. As for the question, is there a specific number for this? There are a specific number, but you're not supposed to know those numbers. Only in polyethylene, we know it's between 500 to 1500. But in this case, the N represents many. So it doesn't mean that you need to know what the exact number the N is. Yeah, please copy this. It's very important that you know how to end the ester. Now the carboxylic end, because always the carboxylic gives the OH, the carboxylic end, you notice it is just C double bond O. The OH is not there, right? It's removed. As for the alcohol end, it is just we are ending with the O. So it's very important you know how to end. That's why I took example to show how the carboxylic end ends and in the alcohol end. So it will be bonded to something else. So don't worry about that. But it's a continuous structure. And this H is removed from the carbo. All is alcohol, the H is removed. Acid, the OH is removed. Don't think because acid is a proton donor, it gives H plus, H is removed from the acid. That's not the case. Always the OH is removed from the acid. We'll be studying the mechanism later on in A levels, right? Then you will know why the H is removed from the alcohol and the OH is removed from the carboxylic acid. Okay, is that clear? Please copy this.
Sir,
Yeah.
there are two Ester linkages in one repeating unit.
No, in one repeating unit there's only one Ester linkage. You can see this is the repeating unit which I have drawn, and in this repeating unit this is the Ester linkage. So if I am to highlight the repeating units here, it will be like this. I'm just going to use green color to highlight the repeating. This is one repeating unit from diol to dicarboxylic. This is another repeating unit from diol to dicarboxylic. This is how the repeating units are. So you can see in one repeating unit you'll only notice one Ester linkage. In one repeating unit you will notice only one Ester linkage. Is that clear? H is removed with OH. That's how the ester is formed, because ester linkage is formed by removal of H with the OH. H of the alcohol, OH of the carboxylic acid. You can write here as, in short, the above polymer can also be represented as. In short, the above polymer may also be represented as, and you can copy the short form which includes the N. Once everyone is done, let me know. What I have written here is, in short, the above polymer can or may also be represented as. In short, the above polymer may also be represented as. Nylon is also condensation polymer. The nylon is formed as a result of the combination of a dicarboxylic acid and a diamine. Now the ester was dicarboxylic acid and diol. Everything is same when it comes to the nylon, which is polyamide, but I already explained how the amide link is formed. That is, just the monomers is what differs. The monomers of the amide is dicarboxylic acid with a diol. So you have a dicarboxylic acid. I'm going to put N in the front to show there's many dicarboxylic acids, right? Many, and many diamines. That's the only difference. The diol is substituted with a diamine when it comes to the nylon polymer, which is polyamide. So I'm going to just highlight the diamine part. So this is dicarboxylic acid, and this is the diamine. So how the amide linkage is formed is that the OH of the dicarboxylic acid is removed with the H of the diamine. Water molecule is lost. Just like the esterification, H was removed from the diol, here H is removed from the diamine. So on the other end, the OH is removed, and this part, the H will be removed, and the polymer will continue. So it's a continuous process. Diamine combines with dicarboxylic always. A dicarboxylic with diamine, and a diamine with dicarboxylic. Right, so you have, I'm going to draw from this end, the dicarboxylic end, put some dotted lines to show it's continuous, and then you have the dicarboxylic here, and then you got the diamine. See, the amide linkage is formed now. This is the amide linkage, right? When this OH is gone with this H, this carbon bonds with this nitrogen. This is the amide linkage. I'm going to highlight the amide linkage here, and whenever the amide linkage is formed, a water molecule is lost. This is the amide or the peptide. Amide or the peptide linkage, water molecule is lost, right? So this is just one repeating unit. So when you draw the polymer, at least more than one repeating unit, you should draw at least 2 or 3 repeating units. The polymer structure, this is one repeating unit, so it continues. You have another dicarboxylic acid, and then the diamine comes there, the second repeating unit. I'm going to just stop with the 3 repeating units. You've got the dicarboxylic acid again, right? And then I'm going to stop with the diamine. So see how I end the diamine, right? So it is H is removed from the amine group. So that's how it ends at the other part. And now this is, you can see, many peptide or many amide linkages. So this is peptide or the amide link. This is the peptide, the amide link. So this nylon, this is structure of nylon. Nylon therefore is known as polypeptide or polyamide. Nylon is known as polypeptide or polyamide or polypeptide. Right? Is that clear? Okay. So I'm going to show the repeating unit now. In short, the above polymer, the whole thing can be represented in short form. So I'm going to show this, the short form. So I can say in short, the above polymer may also be represented as, right? You can show one repeating unit, which is a dicarboxylic acid and diamine. Just one repeating unit. There's one repeating unit. Right, this is one repeating unit, and then you put a square bracket and you put N. Don't forget the N. N shows many repeating units, right? So as for the repeating unit alone, then you draw the structure without the N. The repeating unit will not have the N. So the repeating unit, right? The same structure, one of the each monomer, dicarboxylic and diamine together, just one. That will give you the repeating unit without the N. Don't put the N for the repeating unit. Yeah, of course, if you don't write this N here, N here stands for many, right? But there's a question. So N is nylon, not N is nylon. N is many here. N here means many, and here the N is nitrogen. Of course, the diamine, N is nitrogen. This N is capital N is nitrogen. The simple N here means many. So many dicarboxylic, many diamine gives you the nylon. So this is the whole structure. The polymer is nylon, and if you can see, I will mark the repeating units here. This is one dicarboxylic, one diamine, one dicarboxylic, one diamine. There are 3 repeating units marked in this polymer. So I'm going to take one repeating unit out, which is each of the monomer, and then you put N, you get the polymer. Is that clear? So nylon is the first synthetic fiber produced. It is a condensation polymer made by the reaction between diamine and dicarboxylic acid. Both ends of the monomer are functional groups. An amine group on the first monomer reacts with the carboxylic group on the second monomer to make the amide or the peptide link between the 2 molecules. Each time a link is made, a water molecule is lost. As many peptide or amide linkages are formed during polymerization, nylon is also called as polyamide or polypeptide. Nylon is used in the manufacture of stockings, ropes, fishing lines, parachutes, sleeping bags, etc. And you can copy the detailed structure now. Till then, if you have any questions, any clarifications to be done, please raise your hand. Others can copy. Right, the linkage is the amide linkage or the peptide linkage. So when it comes to condensation polymers, the naming of the polymer is done based on the linkage. So you can't name the polymer based on the monomers because there are 2 different monomers. So the labeling is done using the linkage. So there's many ester linkage, polyester. Many amide linkage, so it's known as polyamide. Can I continue the next question? I hope you finish copying. So next I have shown the diagram how in laboratory how this nylon is synthesized. You have the 2 monomers here. Right, let me just enlarge this diagram. You have 2 monomers, and at the interface of the 2 monomers the polymer nylon is produced. Now you have the second monomer and the first monomer. You have the dicarboxylic acid and diamine, and the point where the 2 monomers meet, the interface, the nylon is produced. So what you do is you just put a rod inside to this interface and slowly pull the rod out and rotate the rod. Rotate the rod, you see the nylon like a small rope getting attracted towards the rod, and you can make a tiny rope of nylon. So this is just a method of making nylon in the laboratory, right? So that's a laboratory synthesis, and all these polymers which we discussed so far, they are actually synthetic polymers, meaning man-made polymers. They are not natural polymers, so therefore they are non-biodegradable. Actually, the non-biodegradable term means natural microorganisms cannot break them down. Because of the strong carbon-carbon bond, natural microorganisms can't break the carbon-carbon bond. That's why we say these polymers are synthetic polymers especially are non-biodegradable. Synthetic polymers are non-biodegradable. Natural microorganisms cannot break them down. So therefore, because they are non-biodegradable, there are so many environmental problems caused by the disposal of these non-biodegradable plastics, because as they don't decay or decompose, they consume a lot of space. So we need to have, especially when you're disposing these plastics, we need to have a lot of landfill space. Landfill sites are required, and if you burn these plastics, a lot of toxic gases are evolved, which causes various health issues as well as global warming. Now, when you heat this, it releases gases such as carbon dioxide, monoxide, and hydrochloric, and a lot of energy as well. So the only solution would be minimize the usage of these plastics and also recycle the plastics whenever possible. Whenever possible, you can recycle plastics, and you can minimize the usage of the plastics. Is that clear? So there are so many issues of disposing the plastics via landfill and incineration. Incineration is burning. So the advantage of just dumping all the plastics to a landfill site is that it's cheapest way to get rid of it, but there are so many environmental issues. But that's the cheapest way to get rid of the plastic. But and also no toxic gases evolve when you just dump it to the landfill site. The main disadvantage is that it needs a lot of landfill area, and also it affects the inhabitants in the area. For example, the bad smell coming out of it, and very unhygienic and with unpleasant scene, and it affects basically the inhabitants in that area. As for incineration erosion, it is burning. Burning is known as incineration. Clear? So as for the incineration method, burning, the advantage and disadvantage is burning uses less space, but that's an advantage. And also the heat produced during burning generates can be used to generate electricity, because a lot of heat is produced when you burn the plastics. As for disadvantages, that overcomes the advantages, in fact. So the disadvantages are toxic gases evolve during this process, and there are greenhouse gases, and also the remnants after heating, the remnants should be buried in the landfill sites. Yeah, of course, it's carcinogen, cancer causing, right? So those are the disadvantage and advantage of disposing the non-biodegradable waste. So as a solution, scientists have now developed biodegradable polyesters. They are biopolyesters. It is, as I mentioned, made from lactic acid obtained by corn, and when lactic acid polymerizes, it forms the biopolymer polylactic acid. So polylactic acid is also known as PLA. So this lactic acid, after some time, can be broken down by the bacteria, because it's basically a starch. It's corn is used there, so the bacteria which is used to break down starch will act on the lactic acid molecules, and eventually it get decomposed. So the PLA, or polylactic acid polymer, which is biodegradable polymer, has a wide variety of applications, such as in medical use. In surgeries, they use for stitches, because these stitches they dissolve after a few days. So that is mainly polylactic acid, and also used for packaging disposable eating utensils and plastic bags. Now they use this type of biodegradable bags. And that's the end of the discussion on the synthetic man-made polymers. As for the natural polymers or biological polymers, there are many. For example, you have the carbohydrates, proteins. They're all natural polymers. And even DNA, deoxyribonucleic acid, is also natural polymer. So you can write some examples for natural polymers here. Right, the first one, carbohydrates. Carbohydrates, and then proteins. Fat is also natural polymer. Carbohydrates, proteins, fat. DNA, carbohydrates, proteins, fat, DNA, and rubber. Yeah, all carbohydrates are polymers, because carbohydrates is a polysaccharide, which is more made out of monosaccharides. Right, glucose, fructose, they polymerizes to form the polysaccharide. right? Right, let's see how the polymerization of amino acids give rise to proteins, right? And we'll compare the structural similarities and differences of nylon and protein. Now the proteins are actually condensation polymer, natural polymer, which is formed by amino acids combined together. Now I'm going to draw you amino acid, show you how amino acid looks like, the structure of it. Any amino acid, it's in fact the building block of the polymer protein, that is the monomer. Any amino acid will contain a carboxylic group attached to a carbon on one end, on the other end amine group attached to a carbon, and you have a hydrogen and an R group. This is amino acid. Now I'm going to substitute the R group with a CH3 here. It can be any group, right? CH3, if it's CH3 we say glycine for this, alanine, I'm sorry, alanine. R can be alkyl group, it can be a CH3 group, C2H5 group, any group. So when this R group differs, it can be a methyl group, ethyl group, the amino acid will differ. So all amino acids contains a carboxylic group, amine group, hydrogen. These three are always there, but only the R group will differ. So because of the difference in the R group, there are about 20 or more, slightly more than 20 different types of amino acids, right? Because R group is different. So let us see how these two amino acids can combine. Sometimes the simplest amino acid can be hydrogen, which is alanine. Don't need to know about these names, right? I'll tell you when to copy. So this is another amino acid. You have carbon here, hydrogen, and a CH3, and this is C double bond O OH. So what happens here, just like the polymerization of the nylon, the amide linkage is formed as a result of the removal of OH from the carboxylic and H from the alcohol, the amine group of another amino acid. This results in the formation of the amide linkage or the peptide linkage. I'm just going to show you how two amino acids can combine. Therefore, that forms a dipeptide. Di means two peptides. Dipeptide is formed this way. If there are many peptide linkages are formed, that's referred to as the polypeptide, which is the protein, which is the polymer. This is not the polymer, this is just a dipeptide. Two peptides and one peptide linkage, in fact. So this is the peptide linkage, the amide linkage. And this molecule is known as a dipeptide. A dipeptide, not that there are two peptide linkages. In a dipeptide, there's only one peptide linkage, but there are two amino acids combining together. Two amino acids combining together in a dipeptide. As for the general formula of the amino acids, there is a general formula of amino acids, but it is, of course, yes, because R group differs. You can't fix a general formula because it differs. But if you have amino acid which is same like R group, only increases by a CH2 group, then you can derive a general formula. Otherwise you cannot. Generally you can't derive a general formula, but you can derive a general structure. You can say amino acids contains this general structure: NH2 attached to carbon, H attached to carboxylic, R group and H group. This is a general structure of amino, not the general formula. Clear? Right. So likewise, this can continue. This is a dipeptide, and this can continue to form polypeptide. Right? It form polypeptide. Is that clear? So proteins are built from amino acid monomers. Each amino acid contains two functional groups, an amine group and a carboxylic group. When two amino acids react together, an amide linkage or a peptide linkage is formed to form a dipeptide, two acids together, two amino acids together, and there are 20 different amino acids different amino acids react to form different proteins. I have not drawn the structure of protein here, just I have shown the dipeptide, which is one peptide linkage and two amino acids referred to as a dipeptide. Just copy this structure. Of course, it can continue again. At the other end, you have another carboxylic acid. It can combine the amine group to form another amide linkage here. So amino acids can combine, different types of amino acids can combine and produce the polypeptide or the polyamide protein. Please copy this. As for the question, is R is always hydrocarbon? No, it can be a hydrocarbon. This group here, it can be hydrocarbon. It cannot. Sometimes it can be even a nitrogen or a carbon or oxygen containing group. So it doesn't matter what only this group will differ. Clear? Okay. So when above process is repeated several times with different amino acids, a polymer is formed. Protein are categorized according to the number of amino acids links. Proteins possess the same linkage, which is amide linkage or peptide linkage, as nylon, but different monomer units. So proteins had the same linkage as the nylon, but different monomers. That's the similarity between the nylon and the protein. The similarity is that they have the same the linkage, which is the amide or the peptide linkage, but the difference between the amino and the nylon and the protein is that the monomer units. Nylon, the monomer is dicarboxylic acid and the diamine. Nylon monomer is dicarboxylic diamine, whereas protein, the monomer is amino acid. So that's the difference between protein and nylon. And for similarity is that they both have share the same amide, the peptide linkage. So you can break down these proteins. The breaking down of protein can be done using water. So breaking down using water is known as hydrolysis, right? And we have studied electrolysis before. Electrolysis is breaking down of a substance using electricity. Likewise, if you break down a substance using water, is referred to as hydrolysis. So hydrolysis can be done by dilute acids or alkalis in water, because water itself cannot be used to hydrolyze because it doesn't have sufficient free H plus and OH minus ions. Therefore, hydrolysis is done via acid hydrolysis or alkali hydrolysis. Either acid or alkali hydrolysis is what we use to break down the proteins. So proteins, I'm going to draw this dipeptide here, which can be hydrolyzed. I think we have, since we have drawn the structure here already, I'm just going to erase this arrow and draw opposite arrow. So this protein can be broken down to their respective the amino acid with the help of acid or alkali. So the backward reaction is what is referred to as the hydrolysis, right? So proteins can be hydrolyzed, meaning broken down into amino acids by heating with dilute acids. This is a reverse reaction of the condensation process. The mixture of amino acids can be separated by chromatography. I think we had discussed this chromatography technique where you have to use an in-hydrogen spray, especially because it is you can't see any spots, because invisible spots. Therefore, we can visualize them using in-hydrogen spray. And chromatography can be used to identify and detect the presence of this amino acid. So you can break down the protein into the corresponding amino acids. You can copy this diagram again on the next question. When you're copying this, first copy the amide and then put an arrow and copy below that the amino acids. First copy the amide, put an arrow down, and below that copy these amino acids. Yeah. So the ester fat is a condensation polymer which is formed as a result of glycerol molecule which is propane 1,2,3 triol, because first, second, and third carbon has the ol, so we say triol, reacting with 3 fatty acid molecules. Now, what is fatty acid? Fatty acid is a long chain carboxylic acid. This is a long chain. I'm going to put a zigzag line to show the long chain. There are so many carbons there. So the long chain I represent by a zigzag line. And so one glycerol molecule reacting with 3 fatty acids. Why 3 fatty acids? Because there are 3 OH groups in the glycerol molecule, which can form 3 ester linkages by reacting with the 3 carboxylic acid. This is known as the carboxylic acid, long chain carboxylic acid, which is known as fatty acid, which is, I write in brackets, long chain carboxylic acid, right? So what happens here? Esterification takes place. The carboxylic gives the OH. OH is removed from the carboxylic. H is removed from the alcohol. 3 water molecules are removed. 3 water molecules are removed, and that will give you the ester, which is fat. Fat in solid form, in liquid form, that is oil, right? So this is the structure of fat oil. That's also a condensation polymer. You can see 3 ester linkages, right? So this is, as this polymer is formed, 3 water molecules are lost, and this is the structure of fat oil. So fat oil condensation polymer is formed as a result of the glycerol molecule, which is propane 1,2,3 triol, 3 OH groups reacting with 3 fatty acid molecules, which is long chain carboxylic. Is that clear? Any questions? Animal fat and vegetable oil are esters of glycerol and fatty acid. Glycerol is an alcohol with 3 OH groups, and fatty acids are long chain carboxylic acids. A glycerol molecule reacts with 3 fatty acid molecules to form the fat, the ester fat. We can copy this molecule now. So the soap is produced as a result of the alkali hydrolysis of the fat, and when you hydrolyze the fat, what happens? You get the glycerol molecule and 3 fatty acid molecules. Actually, these are sodium salt of fatty acid molecule, which is referred to as the soap. Okay, so please copy this. The condensation polymer of carbohydrates. Now the carbohydrates have the monosaccharide, which is the repeating unit. Monosaccharides contain both OH groups. I mean, both the ends you have OH groups of monosaccharides. The structure of monosaccharides are complex, like glucose, fructose, galactose, C6H12O6 is a cyclic molecule. We're not supposed to know the structure of those molecules at this stage. So whatever it is, there are it's a complex structure, and there are 2 OH groups. So what happens here is not ester linkage. What happens here is that OH of one goes with the H of the other. A water molecule is lost. If this molecule OH is removed, it removes with the other molecule's H. So OH of one molecule, H of the other molecule, right? Water molecule is lost. As a result, these 2 molecules combine together. So at this end, the OH is removed. So the structure of the polymer will look like this. right? You have the O like this. Box is a complex structure, so I'm going to end the polymer with a dash, because one end, if OH is removed, the other end, the OH, will be removed, right? So carbohydrate is a compound containing carbon, hydrogen, and oxygen. The ratio is always between the carbon and hydrogen, also the hydrogen and oxygen is 2:1. You can see glucose, the hydrogen and oxygen is 2:1, and sucrose and glucose both 2:1. So simple sugars, monosaccharides, glucose, fructose, galactose are known as monosaccharides. C3 to C7, 3 to 7 carbon atoms, and the condensation polymers of these simple sugar molecules, monosaccharides, produces a long chain polysaccharides known as carbohydrates: starch, glycogen, and cellulose. So this is the monosaccharides, and this is, you get the polysaccharide. Please copy the structure. So simply OH of one molecule goes with the H of the other molecule. This is not ester linkage, this is just the oxygen which links the two monosaccharides together. Please copy this. Like the hydrolysis for others are done, like the proteins and the fat, even the polysaccharides can be hydrolyzed. When you hydrolyze polysaccharides, you get the monomer, the corresponding monomer you get. So this is the polysaccharide, and you can carry out acid hydrolysis, add acid and warm, aqueous acid and warm, you get the monosaccharides again, right? Monosaccharides again. Should you know about soap? Better you know about soaps, because it's just they can give as a question. Better you have idea about how soap is made. So when carbohydrates are digested, they are broken down back to glucose and releases energy in ATP form, and the glucose is then oxidized by respiration. Polysaccharides are broken down in the laboratory by warming with HCl acid. This process is known as acid hydrolysis, and you can copy this there. So the substance in hydrolysis here is just acid and a little bit of acid and water. Aqueous is acid hydrolysis. I mentioned at the beginning, hydrolysis is either acid hydrolysis or the alkali. There's no catalyst used here. The arrow here is just the reaction. This is the pointing towards the product. It's pointing towards the product. Yeah, it's H plus and H2O. H plus H2O means aqueous acid. Aqueous acid. Right, done. Yes. So with that, if everyone is done, we'll conclude for today. Unless you have any questions. Any questions?